interconnection. Okay, can you see the slides on the screen? Okay, good. Right, so we'll continue with interconnections and contacts. We just finished with process integration. Okay, so in the process integration topic, you have seen how do we fabricate the whole flow of CMOS in our case, starting from the bare wafer, okay, the bare wafer, and then the gate aux, the gate, and the following modules till the bond pad, right? Till bond pad and passivation. So now we're going to look at how the interconnects and contacts look like. And we have also discussed briefly, I've shared briefly in our group, in our WhatsApp group, how does a typical interconnects and contacts look like if you're talking about different technologies, right? So I've seen a couple on Intel and Fujitsu, so you can see the variations of the number of metals required, for example. Okay, so you've seen up to say 8, 9 with different kind of architectures, the different kind of configurations and look, but they are all similar in terms of the operation principle. Okay, they're all similar. It's just that each type of interconnect and contact is paired or is tailored or is customized for different process technology. Okay, so and the very same knowledge from the process integration and this interconnections contact can also be adopted and adapted to different semiconductor devices, right? Different fabrication. It's just that the flow will be different because the flow serves for one unique device. Okay, so if you see the flow for solar cell, for example, solar cell, still silicon based, then you can see that the flow is entirely different, but the basic processes used in the fabrications are similar, right? Are similar. It's just that the complexity will be a lot lesser if you compare solar cell to CMOS, for example. Okay, then you will also discover how this process flow will differ for other devices. For example, cadmium telluride solar cells, SSDs, gallium nitride, LEDs, for example, sensors, and all other devices that you're supposed to cover in your group presentation from the 31st of January. Okay, so at that point we'll see how the difference look like between each device with respect to this device that we learned in this course, which is CMOS. Okay, even the CMOS in this course is not covered completely. So as I've said last time, I only showed to you up to metal 2. Okay, but the actual devices may consist up to 7, 8, 9 metal layers, right? And the top or the back end or each layer in the metal layers, say metal 3, metal 4, metal 5. So most of them just repeat themselves, okay, until they reach the top metal. You can see the same sequence we discussed last time when we talk about metal 1, metal 2. So you've seen IMD, you've seen the the plug, the contact edge, and then the plug, and then planarization, and then comes the next step. Okay, so it's not about the exact thing you learn here, but rather what you learn here, then that you can adopt to different devices. In fact, if we talk about just transistors alone, there are already a lot of differences. If we talk about CMOS migrating to, say, FinFET, FinFET migrating to GAA FET, right? Gate all around FET, and fin is the fin that you're supposed to present, right? So you can see the difference in the layers, in the configuration, in the details already. So not talking about other devices yet. So if you go for other devices, of course, you can expect or you should expect a different process flow, but with the same basics, right? Right, so this page challenge what you've learned. So let's go to the first one. I don't want to go to the second one because we have covered this one during our last class. So what are the 5 important modules in CMOS process integration? So what are the 5? Wells, okay. Wells in the front side. Now you can also relate to the schematic down there, right? Even though they don't have the levels. Isolations, okay. 1, 2, 1 well, 2 isolations, okay. How about the remaining 3 modules? Junction, 3. Cool. 2 more. Wells, isolation, junction. Interconnects, right? Interconnects, the one that we're going to cover later today. And the last one, gate stacks, right? Gate stacks, the most important part, the key of the device. Okay, you boleh tengok balik dekat link yang saya hantar dalam WhatsApp tu. If you look at the example, we say 8 metal layers, 9 metal layers. Tengok dekat device tu, the key device is down there, right? It's really at the bottom of the structure or the architecture. The rest are all interconnects. Metal 1 sampai atas semua interconnect, interconnect and contact. Yang the key thing is down there, very small, kadang-kadang tak nampak kan? Hardly noticeable sometimes because they're just too small with respect to the contact. Okay, MOS, okay, more down there, gate and gate aux. Gate aux memang confirm tak nampak langsung. Okay, it's just too thin with respect to metal width and height. Okay, for example. So, okay, kita dah discuss the second part, the name and role of each color-coded region. You should be able to describe the fabrication process used to prepare them, right? Wells pakai apa, tip pakai apa, ya apa ni, shallow layer kat atas tu, for your source and drain pakai proses apa, how is it done, what are the details, you know, the gate, spacer, plug, metal 1, a BPSG, metal 1, IMD 1, plug again, right? Metal 2, preservation, bond pad, at least for this case, for simplicity. Okay, kalau nak ulang, they can just repeat for metal 3, metal 4, 5, up to top metal, and then you end with preservation as well. Okay, so now let's talk about the interconnects. Okay, the interconnects and contacts. So if you talk about metal contacts, you can always relate this to the one that you've learned in the last semester. Remember last time we talked about metal semiconductor junction? Ingat tak? When we talk after, I think after we discuss about PN junction, we talk about metal semiconductor junction, and then we also talk about heterojunction, okay? Heterojunction. So yeah, this is part of the things, right? Part of the device physics or in the 386, okay? So for examples, metal contacts that we use for fabrication, there are a range of different metals that we can use depending on the layer and the intended purpose. For example, you may use silver, aluminium, gold, cobalt, and whatnot. And you can also see the bulk resistivity of the metals. Bulk resistivity of the metals on the second column in micro ohm cm. So when we talk about resistivity of silicon last time, we discussed about doping level against resistivity against doping level curve. If you can recall, we discussed a couple of times. So the typical, if you can recall, the typical magnitude of the semiconductor resistivity is usually in the milliohm region ataupun ohm cm punya region. But if you talk about metal, we're talking about micro ohm. Okay, micro ohm. Tengok unik ke depan ni. Sorry, micro ohm. Sebelum ni we talk about, say, if we talk about p-type in comparison, if we talk about p-type silicon with doping level of 1 times 1016 per centimeter cube, then you're talking about 1 ohm cm kind of resistivity, 1, 2 ohm cm. So when we talk about metal, mula-mula three exit kita discuss metal, insulator, semiconductor kan, in terms of the resistivity against conductivity, the inverse. Conductivity is in the inverse of resistivity. So you can see here, when you compare resistivity of semiconductor, we're talking about ohm cm region, and then the moment you start talking about the metals, then we are talking about micro. Okay, so that's like 6 orders of magnitude lower in terms of resistivity if you compare to semiconductor like silicon, right? So this bulk resistivity will be a very crucial part in choosing which metal to use for your device fabrication. Commonly used metals are aluminum, titanium, tungsten, copper. So you have seen before this, when you talk about the plug, you're talking about tungsten deposition, right? So titanium, we discussed about the silicide formation. Remember, TiSi2, in order to form ohmic contact between your source drain to the metal one. Okay, titanium silicide, and then copper, aluminum are also common. Less frequently utilized, for example, nickel, platinum, palladium. Nickel, less common. Platinum, palladium, of course, because they are so expensive, right? So expensive. If you want to compare, say, if you talk about sputtering process, yang kita pakai dalam non-lab tu, so you can buy that sputter target of that size with the price of about 2,000 ringgit. Kalau you pakai aluminium, it will cost you somewhere around 2,000 ringgit to buy that sputter target. On the other hand, if you talk about PT, PD, platinum, palladium, we're talking about 30,000 ringgit. Okay, so harga 2,000 kat melawan 20,000, 30,000. So that's the price of PT, PD. Super expensive. So kalau you punya project sebelum ni ada buat PT, PD, then you have been using expensive metals for your work. Okay, tak ramai orang pakai because they are simply too expensive. Right, types of contact. Okay, you can see this figure 7.3. Aluminium 2p type silicon forms an ohmic contact. Okay, for example, you can see here aluminium sitting on P or P plus, and then you block some other areas with SL2. And then you mask some area, and then you open certain area for contacting purpose. Maknanya aluminium contact with silicon, whether the silicon is P or P plus, but then you close certain areas from contacting. Okay. For your information, if you talk about device physics, fabrication, if you talk about device physics, if you're talking about metal to semiconductor punya interface, metal to semiconductor, anytime you put metal on semiconductor, say silicon on aluminum, this interface is a very defective interface, highly defective interface. Sebab you letak metal on semiconductor, so it's going to be a defective interface, akan ada recombination and so on and so forth. So one of the strategies that you can do in order to minimize recombination at this interface is by not contacting too much. Okay, maksudnya you nak letak aluminium, but then you don't contact aluminium with the silicon on two wide areas. Okay, on two wide areas. You want to have contact with silicon, but you want to limit the contact area at the same time. Sebab the moment you contact, dia akan jadi defective interface. But yet you have to have the contacts in order to extract carriers or inject carriers and so on and so forth. But you don't want to have too much of them because they're going to be defective. Okay, they're going to be defective. So one strategy is to handle that is by having this masking in other areas. You will see this. Group mana yang buat PERC silicon solar cell? Group 2 ke? Ada satu group yang buat PERC silicon solar cell. You'll get to see this at the rear contact of your device. PERC silicon. Sebab apa tu saya tak nak beritahu lah, bagi group explain lah. But I've given to you the hint already, something to do with recombination, and you want to minimize the contact area between metal and silicon. You want to have the contact, but not too much of the contact. Okay. So, yep. So form ohmic contact depending on the doping level. And then aluminium to N-type, ini P-type, the first one. And aluminium to N-type silicon can form a rectifying contact, Schottky barrier. Okay. Aluminium to N-type will form Schottky barrier. Okay, kita dah belajar this topic last time when I talk about ohmic versus Schottky. I think in the last course. Okay, can you still recall what's the difference between ohmic and Schottky? Anyone can recall? How about the current flow on ohmic if you compare to Schottky? Anyone? Ada yang ingat lagi? 386. Ohmic contact, Schottky contact, IV curve. Dua lah. Okay, Faris. Schottky, one direction. One direction of what? Faris? Apa yang one direction tu? Right, current flow is one direction. That's why we call it rectifying, right? Rectifying. When they rectify on the other side, only allows the current to flow in one direction. Okay. On the other hand, the ohmic is two direction. Okay, so you can have a look at this. If you talk about ohmic, then A will have this sort of IV curve. Oh, sorry. A punya ni, so that means if you talk about aluminium on P or P plus, you're gonna get ohmic. Not necessarily, but it's a lot easier to get ohmic. In some condition, you may have to anneal the contact, right? Anneal maksudnya you bring the sample into a furnace and then heat up the sample at some temperature for some time in certain ambient to get the contact annealed to form a good resistance. Then only you will get ohmic contact. Okay. On the other hand, if you use aluminium on N-type silicon, you're going to get Schottky contact. So it only allows the current to pass through in this region, right? Hence rectifying contact. Okay, kalau you pakai aluminium on N+, you're going to get something like this. It's a bit heavily doped, so that's why you end up like that, right? So recall balik ohmic, Schottky last time. Right, aluminum spiking and junction penetration. What is this? Silicon absorption into aluminium results in aluminium spikes. So when you have your aluminium contact on silicon wafer, right? And then you open certain areas to be contacted. So in this case, you open this area to be contacted, the whole area. And you open this area to be contacted, open these areas to be contacted, and you mask the remaining areas. And then you pattern. To be able to do this, you have to be able to pattern SL2 first. Okay. Then it goes back to the lithography and etching and all those stuff, right? So you pattern the remaining areas. When the aluminium sits on silicon, so there's a tendency for us to get aluminium spiking. Aluminium spiking, apa maksudnya? It's due to silicon absorption into the aluminium. Silicon ni yang ada dekat wafer ni. So some of them, a small portion of them, could be absorbed into the aluminium contact. Silicon masuk aluminium, resulting in aluminium spiking. Spikes can short junctions or cause excess leakage. Okay, as a result, you may have shorts and excess leakage due to the spikes. Right, barrier metal deposited prior to metallization. In order to prevent, what you can do is you can deposit a metal barrier, but then it cannot be too thick because it's got to be insulator kan. Kalau dia it's going to be not so good in terms of conductivity, right? Barrier metal not entirely insulator because it is metal after all. It's just that the conductivity is not as the conductivity of the original aluminium on silicon, because you need to have a material in between, right? So in order to prevent this, also you can do is to do sputter deposition of aluminium with 1% of silicon. Maknanya you dah supply the silicon siap-siap dalam aluminium tu in order to reduce the spiking probability, right? So you can see here, aluminum spikes, and then if you have junction, katakanlah you ada junction, say this one is P-type, this was N-type, or vice versa. And then if the aluminum spikes, then you akan dapat leakage. Dan dia akan cross the junction short. Okay, short. So the moment when you, if you can recall last time, when they talk about PN junction, PN, okay, we supposed to have metal contact on the N side, and we also supposed to have metal contact on the P side, right? So electrically, the contacts on the N side will only interact with the carriers or with the semiconductor on the N side. And the same thing is also applicable for the P side. The metal contact on the P side is supposed to interact with the semiconductor or the carriers in the P-type, on the P-type, right? Tapi when you have spiking, if just imagine if your PN is too thin, tak tebal mana, it's not that thick, then you have spiking, for example. Contoh, if your layer is thick, if this P and N are thick, it's the probability is not that high because it's not that easy to have spike either. But if you're working with a very thin device where your thickness of N and thickness of P are equally small, and then a little spiking into the semiconductors can short the junction. Okay, can short the junction. Tapi kalau device too thick and your P and N are equally thick or both thick, then it's harder to happen. But normally we normally have if you're working on wafer, for example, wafer is relatively thick. Say you're working with 400 micron of silicon, that is relatively thick. If you have a junction kat belakang ni, to spike to the front, if you have your junction in the front, your silicon is P-type and then your diffuse junction is N-type. This front layer is usually thin, right? Thin here. It could be in the region of 50 nano, 100, 200. So that is considered quite thin. If you compare to the 400 micron, of course, right? So this is only 200 nanometer, okay, nanometer. 1,000 times smaller in magnitude if you compare to 400 micron, right? 10 to minus 9 versus 10 minus 6. So in that case, if you have spiking on the front, so maksudnya ada possibility for the short, junction short to happen, right? So you have to check on this and be aware on this. So kadang-kadang you buat device, you buat experiment, you dapat curve a bit weird or performance drops or something. Kadang-kadang it's not due to the fabrication tak jadi ke apa ke, kadang-kadang it's just due to the short. But you have to know what are the symptoms of shorts in your device, okay? Okay, alloying of contacts. Most of the time, this one happens. For example, we have been talking about alloying of contacts when we talk about process integration. Titanium, then you anneal at high temperature in RTP, and then in some ambient, and then you're gonna get the alloy of titanium and silicate, titanium silicide, TiSiO2, right? Si2. Okay, so those are alloying. One of the examples of alloying that we are talking here. So the purpose of alloy is to obtain very low contact resistivity. Okay, low contact resistivity. That means if you have your silicon here, if you have, say, titanium, and then you don't do anything to titanium, that you tend to get high contact resistance because it's not annealed, right? Maksudnya titanium tu macam dia duduk just independently on silicon and it doesn't really go in to form a good contact. On the other hand, if you anneal, you can get some portion of the titanium into silicon, which improves the overall contact resistivity. Improves here means reduce resistivity. You want to have small contact resistivity between metal and semiconductor. Okay, so you can see here contact resistance on the Y within 10 minus 1 to 10 minus 6 ohm cm squared against temperature, okay, of alloying, alloying temperature. You can alloy at this temperature. So tengok apa jadi. So generally you can see that if you go for higher temperature, you're going to get lower contact resistivity, right? So they go down because of improved resistance. Some part of the contact goes into the silicon and then forming good conductivity, right? So specific contact resistivity, contact resistance, and you can then calculate contact resistance by your specific contact resistivity on the y-axis over the area of the contact, okay, over the area. So rho C over A, then you're going to get your RC, contact resistance. So that's how you calculate. Okay, one issue that we have when we talk about interconnect is called electromigration. Electromigration. So what is this electromigration? Electromigration is transport of material caused by gradual movement of ions in a conductor due to momentum transfer between conducting electrons and diffusing metal atoms, right? Okay. Transport of material. So we're talking about the movement or the transport of material within your wires, within your conductor. In this case, we're talking about aluminium ke, copper ke, but they form the contact on the device, right? Or part of the device. So dalam conductor tu, there's this issue called electromigration. Ada movement, gradual movement of ions in a conductor. Conductor in this case bukan wire ni, but then the interconnects themselves due to momentum transfer between conducting electrons and diffusing metal atoms. So ada momentum transfer within the interconnect. Ada actually some physics within. Okay, so nampak macam everything is good, but then there are electromigrations going on. So leads to reliability issue in the device. Okay, kita akan tengok what happens during electromigration. It's gonna break the whole interconnect. It can break partly, or the worst case, the whole thing, right? Electromigration in a gold nanowire. Let me just show you this. So let me share with you. Yeah. Skip ad. Yeah, saya buka YouTube dulu. Alright, so let me share with you YouTube. Share. Okay, can you see the YouTube punya window? Right, okay, so let's just play this. Just a short while, 30 seconds. Yeah. The electromigration. In electromigration of a gold nanowire, a small wire made of gold. Look at what's happening. Ada shape change. Nampak dia kat tengah ni. Ada electromigration. So atom dia gone. So finally it breaks the whole wire. Okay. Ulang 9 minit kat tengah ni. So you can see it starts forming electromigration. Dan nampak dia punya gold wire tu dah atom dia transported, dia macam ada pergerakan, and eventually the kat tengah tu is the small area of the contact is gone. Okay, it's gone and then it breaks the whole thing. It breaks the whole thing, right? So maknanya you tak dapat ada, you punya contact will be disconnected in the center due to electromigration. So what is this electromigration? Share again. Okay, can you see the slides again? All right, good. Okay, so kita ulang balik. Transport of material caused by gradual movement of ions in a conductor in the interconnects due to momentum transfer between conducting electrons and the fusing metal atoms. So the momentum transfer, even though the mass is really small, but then ada momentum, right? Ada momentum there. So if it breaks, and then your device will not be functional anymore, and that leads to reliability issue. Okay, dalam semiconductor fab front end ke ataupun back end ke, there are always departments called FA and reliability, right? So mungkin dia panggil different name lah, but then the essence of the works are in the failure analysis and then the reliability of your products, of your devices. Okay, so dia akan these departments are the one who are responsible for the failure analysis, including this electromigration. Check kalau ada failure, then what is it due to? Dia akan buat cross section, dia akan hantar macam benda siasat lah, more or less. They're going to do the diagnostic of the failure of the issues, and then they're trying to report. They will report and talk to the main processes modules, main module, litho ke etch ke whatever, a metal deposition, and try to fix the problem, right? So FA and reliability. So electromigration, tengok apa jadi. Electromigration is due to momentum transfer from the electrons moving in a wire. Okay, this is your wire, for example. That's your wire, and then the copper ions movement, and then you have movement of electrons as well. Okay, so this movement lead to momentum transfer. Okay, momentum transfer. So especially if we talk about high current density, right? High current density. So you just have a very small interconnect, small wire that can carry current over a unit area, So if you talk about the current density J, so that will be equal to 1 over A, right? A is your cross section of the wire. So depending on the size of the interconnect. So high current density causes voids to form in the interconnects. So void. Bila lagi besar current, so you push high current through a small area, dia jadi it's going to be very big. So they can cause more electromigration because the pressure, if you like, dia punya current carrying capability to through a very small area is has to be very huge. Okay, so this causes electron wind. We call it electron wind. Macam angin electron, due to the gradual movement of the ions and electrons causes movement of metal atoms. Okay, so this electron wind, due to the current carrying mechanism in the conductor, causes movement of metal atom. Ada momentum there. So as a result, it's going to cause the breakage or metal contact at some point. Okay, so this will be more serious if you talk about small ataupun yang high technology punya technology where your interconnect has to be very dense, right, and small. So it's going to be causing more electromigration. Okay, so bila conductor ni breaks kat tengah ni, then that's it. Then the wires are no longer connected. Okay, no longer connected. So SEM shows aluminium interconnection failure caused by electromigration. Aluminium interconnect caused by electromigration. Sputtered aluminium with 0.5% copper. This one is A. And then evaporated aluminium with 0.5% copper. Dua ada copper, but then still suffering from electromigration. So in this case, if we talk about current density J, assuming the current is about 1 amp passing through 1 micron squared of a conductor or interconnect, and then the J will be amounting up to about 1 mega ampere per cm squared, right? 1 mega amp, super high, super high current density, because you're talking about relatively high ampere, 1 amp, over a very small interconnect, right? So the J2 will be very, very huge. Okay, so the current carrying capability of the conductor has to be very huge with good reliability. Okay, so 1 mega ohm. Walaupun current is only like 1 amp, but then due to the small area, then uh, it's carrying 1 mega ohm, not 1 mega ohm, 1 mega amp of current per cm squared, right? So when we talk about electromigration, we are talking about Black's equation, mathematical model for the mean time to failure. Mean time to failure. Berapa lama dia boleh tahan before it breaks, right? Sebelum dia fail. When you join your internship later on ataupun your first job, you're going to be talking a lot on this mean time to failure. Mean time to failure. Some even say MTTF, mean time to failure. If you're running equipment, for example, if you're in charge of equipment, then you'll probably be talking about MTBI, mean time between interruption. Maknanya dia nak quantify how long your equipments are up and running before the next interruption, before it's down. Right? MTBI has to be kept high because you wanna make sure that the equipment's having high uptime before it goes down due to whatever reason, right? MTBI. MTBI, MTTF, MTTR, I think. You boleh search nanti daripada sini, you can just search mean time MTBR or MTTR, MTBR, I think. Mean time between repair. Equipment repair, yeah. So, well, you're going to be talking a lot on this MT thing. MT. And you search. If you are joining equipment engineering team, then these are some of the metrics that you're going to be focusing on, doing the analysis, make sure things are better and better over time, right? So when I talk about this Black equation, then we're talking about mean time to failure, right? The time it takes before it fails due to electromigration, right? For example, if you talk about this, if you look at the schematic, sorry, the graph on the left, so it shows electromigration performance improvement using copper metallization. So if you talk about aluminium copper contact, the control punya sample, okay, then you can see cumulative failure percent on the y-axis against MTTF, right? Mean time to failure, arbitrary unit. So if you have if you use this ALCU, aluminum copper contact or interconnect as your control, this is the typical shape of your graph, right? Cumulative failures against time. On the other hand, if you move to copper, then your lifetime increases by 10 times. And you switch to copper instead of ALCU, your lifetime of the contacts lasts for, so it increases by 10 times. So that means cumulative failure shape is about the same. Positive slope, steepness pun lebih kurang, lebih kurang, but then the time it takes is like here is 10, here is like 200, right? 200 at least. So 10 times just by switching to copper metallization instead of aluminum metallization. So that's why choosing the right metals for your process is equally important as the front end side of the fabrication, right? Copper added to aluminum to improve lifetime. Yep, you can add on, and this is the equation: 1 over J squared exponential EA over KT, current density, EA is activation energy, and MTF is mean time to failure. Heavier metals, for example, copper, have low activation energy. Okay, you can switch to heavier metals, for example, to copper in order to increase the lifetime of your contacts, of your interconnects. Okay, other examples we've discussed on silicide. Okay, the other architecture that's available for us to learn. It can be ALCU metallization, and then you can have this silicide, barrier metal. Silicides are noble and refractory metal. We discussed about TiSi2. Can be used to reduce sheet resistance of polysilicon and diffuse interconnect. So kita dah tengok ni waktu proses integration, right? TiSi2, Si2 provide shunting layer in parallel with original interconnection, right? So there are many roles that can be played by the silicides. The examples of silicides, banyak choice. You can use some silicide of interest. You can use cobalt, disilicide, hafnium, molybdenum, nickel, palladium, platinum, tantalum, titanium, tungsten, zirconium. So banyak choice, huh? So this one is the configurations: metal and polysilicon, co-sputtered alloy, blah blah blah. The temperature that they need to be sintered. Sintered mean macam anil lah. Bila you deposit, then you have to treat at that temperature. Or sintered, we call it sintered. Some other cases we call them anneal, boleh juga, right? In order to ensure good shear resistance or reduce shear resistance between the metal to the semiconductor, right? That's why we call it cobalt disilicide, hafnium silicide, molybdenum silicide, silicide. So interaction as a result of interaction between the metals to the silicon, right? This one is the phase diagram. You can cross-check the phase diagram of eutectic temperature. Okay. Specific resistivity in micro ohm cm as well. Okay. Micro ohm. Right, another form called salicide, self-aligned silicide on polysilicon. Okay. Often termed salicide. There are banyak contact configuration that we can use when we talk about MOSFET. Okay. Nanti let's explore how does the contact or the interconnect look like on FinFET in comparison to this. FinFET, ada group of FinFET kan? There's no group doing GAA FET, right? But anyways, okay, we can just look at FinFET and see how's it different, how many metal layers are required, how many metal masks are required for the process. Kita akan tengok dalam process flow ni. One of the sections that you're supposed to present later on, the process flow. So you can see here many different configuration. Use of self-aligned silicide or silicide on MOS, okay, metal oxide semiconductor device. A is oxide deposited over normal MOS structure following polysilicon deposition, right? Ini macam ni. Kalau B pula structure after RIE living sidewall oxide spacer. Ini RIE kat sini. Living subspacer. So what is C? Metal deposited over the structure and heated to form. So silicide, ni metal deposited, then you anneal. So banyak cara. Unreacted metals readily etch away, right? Ini pun boleh. Alright. Interconnect silicides in devices. This is more complicated. So let's see, you have in this case ALCU, titanium tungsten alloy, and then you have your silicide here, right? Platinum silicide, PTSI. You can cari yang SI kat belakang. So that's where it is. It sits below the contact, between the collector and the buried layer, right? Between collector and buried layer N+. On the other hand, the next example is for MSI and palladium, palladium, right? For in bipolar and MOS devices. These are some of the examples. Interconnects. For interconnects, some processes require lift off. Okay, lift off process. Okay, to be able to do this, you have two options. Only lift off. Okay, the first one, if you look at A on the left, you deposit metal on the wafer, right? How to do that? We deposit metal on the wafer, and then you deposit and pattern the resist on the metal. So you define the metal to be patterned by using photoresist, and then you etch. Okay, say this one is this metal is aluminium. Then you put the resist, you pattern resist on aluminium, and then you etch aluminium. You remove the resist, you etch aluminium, you remove the resist, then you're going to be left with patterned aluminium, okay, on the left, by process number 1. and that's called subtractive etching process. Maknanya you deposit blanket metal, then you do lithography to define the pattern, and then you etch, and then that's called subtractive etching process. The other option is you pattern the resist first on the wafer, pattern resist, then provide opening in the center, and then you deposit your film blanket. So maknanya yang exposed area ni will be deposited on the wafer, and then yang mask area will be deposited on the resist, and then you lift off the whole resist. You remove the resist, you etch resist, dia punya atas akan terkeluar sekali to produce pattern AL as well. Okay, so this one is called additive metal liftoff. So this is trying to show you that if you want to do this, if you want to fabricate this pattern aluminum, you can either approach the process from process 1, which is subtractive etching process, and you just do blanket metal and then you define the resist and you etch. Or the other one, you can also do metal lift off process, where you define the resist first, deposit the metal and lift off the resist. Dua-dua pun bagi the same result, same result, but you can approach through two ways at least for this case. So when you talk about other fabrication dalam device fabrication, you can always approach things from many angles. So maksudnya, it's not necessarily one fixed process that you have to do in order to get something. It's always a combination of something, like what we discussed during the case study of lithography, right? So you can either do RIE isotropic to scale down the polysilicon gate, and then before you do something else, RIE anisotropic and stuff like that, and eventually plasma etching of the resist in order to remove the resist and leave your polysilicon with smaller size on your device. Or you can either do with whatever you have, whatever lithography that you have, but you do multi-patterning, right? We discussed that. So you can also approach multi-patterning, but you have to do the process twice, right? You do the process for 200 nanometer, for example, and then you come back after etch. You come back in the next CED, and then you don't have to coat the resist, but you just etch. You just exposed the existing pattern with 200 nanometer halfway, so that you can develop halfway, and then you are left with the 100 nanometer with remaining polysilicon. So those are the examples of how you can approach fabrication from different angles. So the same like this lift-off process. Okay, multi-level metallization, another example. This one really depends on what sort of metallization do you have. You can also go multi-level. So two-level metal processes in this case, and then silicon dioxide, polyimide, or silicon nitride is used as dielectric. So you can see here, this one is SiO2. This one is also SiO2. You can also use nitride or polyimide depending on the constraint of the process. Vias form to connect between metal layers. So yep, so we have talked about that last time when we talked about metal 1. Then you want to connect that, metal, and then you connect through VR to the next metal, VR to the next metal, somewhat like that. So VRs can be filled to improve planarization, right? When the moment you've done a deposition of tungsten in the VRs, you can then CMP to planarize before we move on to the next process, right? So example of multi-level metallization we've discussed in the group as well. You have seen Fujitsu, you've seen Intel's, you've seen a couple more examples of multi-level metallization up to a couple metal layers. So in this case, how many do we have? So if you look at this SEM, how many do we have? How many layers do we have? How many metal layers? Berapa tu? Multi-level aluminum metallization via tungsten plugs, then planarized by CMP. Tengok kat mana dia punya gate. Where's the gate? Where's the gate? This is your gate. Small one. Gate. Then this and this source drain. Okay? Gate, source drain. And this is your contact. Contact to the first metal layer, second, third, fourth, fifth. Okay? Ini 5 metal. M5. 5M, right? For example, so the heart of the device is down there, and the rest are all metalizations. Copper interconnects, you can see how is it different from aluminum interconnects, for example. Okay, replacing aluminum wiring in chips had been thought by most to be impossible for a number of technical reasons. So we used to start with aluminum wiring, and then when they tried to move on to some other materials for interconnects, they thought it was impossible. However, IBM team overcame those technical problems, bringing copper wires, right? It started off with aluminum, now copper wires into production, giving an immediate boost to chip performance, right? So back then, 1920, 2009, 2010, 2009, 2008, Silterra adopted copper processing as well, based on the technology transferred from IMEC in Belgium. So at that time, quite a number of engineers were sent to Belgium, IMEC in Belgium, for training, 6 months, 9 months, 3 months, a couple of times. Some came back and then went back to Belgium for the technology transfer of this particular technology, copper technology, right? Where you have to run. Last time I told you about the cross-contamination thing. The moment you ran copper on one equipment, you have to stop and do the cleaning of the copper before you switch to the conventional technology, because you don't want to have cross-contamination that will kill the devices. Okay, so those are the times when Silterra started running copper. It was quite hectic the moment the first time it was adopted. Okay, you switch another copper to another copper, there has to be a downtime and verification to make sure that the copper left in the equipment, on the robots and everything is below the threshold level, below the spec limit, right? Well, more than that or close to that, you cannot release the equipment or the process to run conventional technology or non-copper technologies. Okay, gonna verify, right? Sometimes you did the cleaning and then you ran the XRF. The XRF was used, total X-ray fluorescence characterization, to check for the metal contaminants, the level, sensitivities, and the rest. Kalau dia punya level tu close to the spec, close to the limit, then you have to redo the cleaning for like 1-2 hours, then run test wafers through the equipment, verify, see the latest level of copper and the rest. Okay, then only release to run conventional technologies. This is the operation and the logistics side of running different technologies on one equipment, because you don't have the money to spend on other new equipments just to run copper where the volume might not be big. Okay, so instead you just run multiple technologies, copper and non-copper, on the same equipment, and you have to impose procedures to be able to control cross-contamination. Okay, so plated copper, for example, the process that you have to run, masking material, you have a seed layer, and then you plate the copper, and then you do the lift off, right? You have to do the lift off. Copper deposited using standard plating process adapted to microelectronics. Then a seed layer is deposited. This is the process flow pretty much. And you plate the copper, and then you remove the mask, and then you have your copper on the seed, right? Copper on the seed on the substrate. So this one process flow they can do. Another process called copper damascene process. 155 dah. Copper damascene process. So where you coat your seed on the insulator, then you plate copper, you planarize copper. Okay, you plate copper and then you remove, you CMP the copper, then you're gonna get a planarized copper surface, right? Damascene process used to obtain highly planar surfaces. Kalau you pergi Silterra, then there's going to be one training room named Damascene. Okay, there's a training room named after process name, right? Damascene, whatever. Saya lupa lah, tapi I still remember this Damascene training room. Jadi kalau you masuk awal, you will be trained in the training room for like a few weeks. So one of the training rooms is named Damascene. So dielectric layer, insulator, deposited and pattern, this one, and then seed layer is deposited, and then you plate, and then you polish by CMP. This is another process to do Damascene. So this is the whole copper interconnect if you want to compare to metal, but this one is not that complicated, right? So just one example, just to show to you how does it look like, right? Damascene process flow, dual Damascene process flow. Okay, you have your copper layer down there. So these are the two steps. Detailed the caption, caption. Yeah, still same thing. Damascene process with nitride barrier layer, another configuration. So copper is dalam semua copper. Copper. Yep. Another example. This one a real life example of from SEM cross section is FISM. If you run a copper process, so your device is down here, device is down here, and then you have your metal one, ALCU, metal two, ALCU, ALCU. Then you have vias in between, ALCU, and SiOF, low K dielectric, and a layer of nitride, metal 5, copper. Then you have this Damascene yang kita tengok dalam previous slide tadi, dual Damascene process. So that's how it looks like. So dual Damascene combining aluminium, copper, and tungsten plugs on the lower level. So the plugs are tungsten, just like what we discussed before. So that's the one on the left. And then on the right, dual Damascene copper. Okay, that's how it looks like. Very nice stack of copper Damascene from Motorola. Oh, finish. Right, so we finished the metal and interconnects today. And that means we also done with the syllabus of this course. So however, we still have your assignment 2, right? Assignment 2 is due on 26, 2 more days. 26, and then we're going to start your presentation on the 31st. So that'll be next week. Okay, that'll be next week. Okay, for the presentation, if you don't want to extend that to the following Monday, February, so we can also schedule on the day where we don't have classes, but on the afternoon, if you're free. Okay, for example, kita punya class on Monday will be on 1 to 2, and Tuesday we have 11 to 12. Wednesday, Friday we don't have, no, Wednesday, Thursday, Friday we don't have classes. But will you be free on the afternoon of Monday, Thursday, or Friday, just to get things done within a week? Or you have something going on the afternoon? Or kita kena extend into the following week on the 7th, on Monday, to finish off the final presentation. Are you free on Thursday, Friday? Or Wednesday, Thursday, Friday, sorry. Will you be free or you have classes on the afternoon? They continue, then we're going to be done next week. On the 3rd, yeah? On the 3rd, we cannot do that. Yeah, I'll be free Wednesday and Friday. So, will you be available Wednesday and Friday afternoon? Free ke? Ke ada yang ada kelas? Or ada something else? Free. Ada yang ada something? Friday cannot. Okay then. Wednesday afternoon? Is everyone free? If yes, we can schedule a session, maybe 2 to 3 perhaps, 3 or 4. Free. Yang lain ada tak free Wednesday Wednesday afternoon, say 3 to 4, 2 hari bulan. 2 hari bulan 2. It's cuti kan? Chinese New Year kan? Lupa lah, sorry. Saya ingat Chinese New Year sehari je lah, sorry. Forgot. So no choice then. Okay, then 7, no choice. Saya ingat kan cuti sehari, cuti 2 hari. Ya Allah. Okay lah, tak upaya lah. Okay, if that's the case, then Monday 1 to 2. as the for the final group. All right. Okay, any questions so far? So we've done the syllabus. Hari ni hari apa? Hari Senin. Hari Senin kan. So that means there's no more class until I'll see you in the presentation session. So hari minggu ni tak ada kelas. There's no class tomorrow. There's no class on this Friday as well. But I'll see you Monday next week for the presentation. So please use your class times for the preparation, for the finishing of your assignment 2 and for discussion of your group presentation. Okay? So any questions? Ada? Right, if that's the case, then I'll see you next week, yeah? Okay, don't forget your assignment 2 is due on the 26th, and then get yourself prepared for your assignment 2. No, present the group presentation starting from next Monday. So I'll see you then. Bye-bye. Assalamualaikum. Take care.